In Part 4 of Lecture 3, we will discuss designing an operating system. Designing anything usually starts with deciding what your design parameters are. This is just as true when you are designing an operating system as it is when you are designing an automobile, although the design parameters are obviously different. What these parameters will be depends very heavily on a couple of factors. Firstly, it depends on the hardware that the operating system will support. We saw this in the case of DOS, whose key characteristics were determined very heavily by its being implemented on an IBM PC built around the Intel 8088 microprocessor. This will be true of most operating systems. Even the Unix operating system, which was designed to be as platform independent as any operating system was designed around the so-called target architecture, which was originally the PDP-7 and later changed to the PDP-11 family, VAX-11 family, and 3B2 family. After choosing the hardware, the type of operating system must be determined. Will it be multi-user or single-user? Single-tasking or multitasking? Batch or interactive? Distributive or standalone? Real-time or general purpose? Once these decisions have been made, then the design parameters can be chosen. Design goals can be divided into those that the user would want and those that the system needs to do its job in the way that the designer envisions. The user wants a system that is fast, easy, and convenient to use. The system designer wants the system to be easy to design and maintain, flexible, so it can be modified as necessary, and efficient. Unfortunately, while these are worthy goals, they are also quite vague. Without some metric to quantify, it will be quite difficult to use these as design goals. There are some decisions that operating system designers make that will determine what the system will do. This may affect the features that the system shall include. Whether a system is interactive or batch is such a decision. So is the time slice of a time-sharing system. These are examples of policies. If we decide how we will implement this, such as deciding whether or not to use a timer to preempt a process from the CPU, it is the mechanism that we are choosing. Separating policy and mechanism is a good idea because it results in a more flexible operating system. For example, consider the issue of CPU scheduling. Unix uses a priority queue, where a process's place in line depends on how low a priority number it has. The lower the priority, the nearer it is to the front of the line. This is an example of a mechanism. But who should be pushed to the front of the line? Processes that need a lot of CPU time, or processes that don't have such heavy CPU requirements because they are doing mostly input and output? This decision is essentially a policy issue. Unix generally pushes the input-output intensive processes to the front of the line because it increases input. But this is for all practical purposes a policy decision. Originally, operating systems were all written in assembly language, because only assembly language gave the programmer all the features that they needed in order to implement an operating system. But this is no longer the case. The first operating system written in a higher level language was Burroughs' MCP, or Master Control Program. Multics, the MIT operating system which inspired the design of Unix, was written in PL1. Prime's Primos system was written in Fortran. Dex Ristus was written in BASIC. But most current operating systems, such as Unix, Windows, are now written either in C or C++. Using a higher level language makes it easier to develop code that is more likely to be bug-free. And a language like C or C++ supports all the features that are needed in implementing an operating system, such as structures, arrays, pointers, and so on. The only thing that you can't do in C or C++ that you could do in assembler is to load values into specific registers. And this requires only a minimal amount of assembly coding. The last public domain release of Unix consisted of 10,000 lines of C and 1,000 lines of assembler. Only half were written in assembler because they had to be. The other half were written in assembler for efficiency, not out of necessity. Windows 98 came on a set of disks with its own installation program, which could detect whatever devices you had, and then it would install itself. But operating systems for larger computers don't come this way. Typically what you get is a distribution tape or disk, which has the operating system in source code form, or perhaps precompiled. But it isn't ready to load in that form. The system's authors do not know what a particular system's hardware configuration includes. Which CPU does the computer have? How much memory? What disk drives? What terminals? Up to how many processes will it allow? Once these questions are answered, certain system tables can be created and the system loaded on the computer. This is all usually done these days with the aid of a system generation program, or sysgen for short. It may involve compiling the operating system, or simply loading the proper files and creating the needed tables. But this is a necessary step in getting the operating system ready and running on the computer.